A pleasant day to you. I am Cledera, and I will be discussing a bioassay technique on antidiuretics. Let's have a quick review. Antidiuretics are a class of drugs used to reduce the excretion of urine in the body. Polyuria, or the frequent passage of large volumes of urine, is one of the three most common symptoms of diabetes. Antidiuretics are most commonly used to address polyuria. The article that we will be discussing today is entitled Antidiuretic Activity of the Methanol Extract of Aporusa lindleyana Wight from the family Euphorbiacea in rats, published in July 2014 in the Tropical Journal of Pharmaceutical Research. The authors, who are all Sri Lankan, are Susantha K. Ganegamage, Thusitha U. Abeytunga, and Wanigasekara D. Ratnasooriya. Please take note that one of the authors, Ratnasooriya, has been the principal investigator in two studies on the antidiuretic activity of two different plants in 2003 and 2010, so Ratnasooriya is very much familiar with this procedure. The study was conducted in the University of Colombo in Sri Lanka. The researchers aimed to determine the diuretic activity of Aporusa lindleyana in rats following its claimed use in Sri Lankan traditional medicine by using a methanolic extract of the said plant sample. Let's move on to the methodology. The plant sample was obtained from the Pinadua Medicinal Garden in Sri Lanka. The samples were validated by the Department of Plant Science in the University of Colombo. The plant parts used for the experiment were leaves and barks of the plant. The plant parts were macerated using petroleum ether to defat the sample, and then was extracted using methanol by reflux on a water bath. A rotary evaporator was then used to concentrate the reflux methanol portion at 40 degrees Celsius. The resulting semi-solid residue was then freeze-dried at -58 degrees Celsius to obtain a completely dry solid, which was stored in airtight containers at -20 degrees Celsius prior to use. Using the methanol extract, a well-formulated homogeneous water suspension was prepared for the experiment proper 5 to 10 minutes before use. The researchers did not outline how the doses of the extracts were computed, but reference journals of the study indicated that bioassays of antidiuretic activity regularly use low, mid, and high doses. Previous studies rationalized the highest dose being selected as being 10 times greater than the recommended therapeutic dose because the metabolic rate of rats is greater than that of humans, as indicated in the Laboratory Manual of Pharmacological Evaluation of Natural Products by Baillon. The animal samples used were healthy, adult Sprague Dolly female rats weighing 180 to 250 grams. They were kept in groups of 6 in plastic cages in an animal house maintained at a temperature of 28 to 32 degrees Celsius, relative humidity of 50 to 55%, and a photo period of approximately 12 hours of natural light per day. The rats were given free access to food pellets and clear drinking water. It is unspecified what type of drinking water was used for the animals prior to the actual bioassay procedure. As mentioned earlier, methanol was used as the extracting solvent for A. lindleyana. Because they also want to determine whether it is an antidiuretic or a diuretic, they use furosemide as the diuretic reference or negative control and vasopressin or antidiuretic hormone as the antidiuretic reference or positive control. They also use distilled water as blank. For the actual bioassay method, 49 rats were deprived of water for 18 hours before being orally administered with 15 ml of saline solution or 0.9% weight in volume sodium chloride to ensure water load is uniform. After 45 minutes, their bladders were emptied using pelvic compression and pulling of their tails. The rats were then randomly divided into 6 groups. Group 1 with 6 rats was intraperitoneally given 0.13 ml of antidiuretic hormone or vasopressin per rat. Group 2 with 6 rats was orally given 13 mg per kilogram of furosemide. Group 3 with 6 rats was orally given 500 mg per kilogram of the methanolic extract or ME. Group 4 with 5 rats was orally given 1000 mg per kilogram of ME. Group 5 with 5 rats was orally given 1500 mg per kilogram of ME. Lastly, Group 6 with 21 rats was given 2 ml of distilled water per rat. The researchers did not mention how the actual urine collection was performed, but previous studies involving rat diuresis headed by author Ratnasooriya in 2003 and 2010 indicated the use of metabolic cages. Furthermore, in other related procedures performed in the study, Ganegamage et al. Have indicated use of metabolic cages, further implying that rats were placed in individual metabolic cages. On the right side is an illustration of a metabolic cage. The urine outputs of the rats were measured hourly for 6 hours, starting with the administration of saline solution to the rats. The antidiuretic or diuretic activity of the rats were then determined using the following parameters. Diuretic or antidiuretic activity was determined as the ratio of urinary output of treated to control group. Diuretic potency as ratio of urinary output of treated to reference group. Urinary excretion as the ratio of total urinary output to total volume of liquid administered. Saline excreted as the ratio of urine volume excreted to volume of saline loaded. And change in urine output as the ratio of increased or decreased urine volume to urinary output of control group. All of these were expressed as a percentage. Other tests were also performed aside from the bioassay procedure from the previous slides. To evaluate the mechanism of action of the extract, urine samples collected for the 500 mg per kilogram dose were tested for leukocytes, nitrite, urobilinogen, protein, blood, specific gravity, ketone, bilirubin, glucose, electrolytes such as sodium, potassium, magnesium, and calcium ions. And in addition, the urine samples were tested for conductivity, pH, and diuretic indices. Instruments used were the urine test kit, AAS or atomic absorption spectrophotometer, conductivity meter, and pH meter. In the estimation of creatinine clearance, a different set of rats was used. Preparation of the rats was the same as that of the evaluation of diuretic activity and ensuring uniform load for the rats. Afterwards, the rats were divided into 2 groups with 5 rats per group. To the first group of rats, 500 mg per kilogram of ME was orally administered, and to the second group of rats, 2 ml of distilled water was orally administered. After the measurement of total urine output, blood was extracted from the tail and serum was tested for creatinine to compute for the glomerular filtration rate. To also ensure safety in human use, the researchers conducted an evaluation of acute and subchronic toxicity. Another set of 12 rats were then randomly divided into 2 groups with 6 rats each. To the first group of rats, 2 ml of distilled water was orally administered, and to the second group of rats, the highest dose of the extract, or 1,500 mg per kilogram, was orally administered. Both groups of rats were then observed for 30 days for overt signs of toxicity. After 30 days, the rats were anesthetized using diethyl ether and the blood was withdrawn from the tails. The blood was centrifuged and the serum layer obtained was tested for alanine transaminase, aspartate transaminase, urea, and creatinine levels. Although I did not include it in the PowerPoint, the methanolic extracts were also subjected to phytochemical tests for the presence of alkaloids, flavonoids, phenols, coumarins, steroids, saponins, tannins, amino acids, and peptides as described by Fong's phytochemical methods. Let's discuss the results of the evaluation of diuretic or antidiuretic activity. In the percent change of urine volume, we can see that all of the methanolic extracts lower the urine volume, thus categorizing A. lindleyana as an antidiuretic rather than a diuretic. Next to vasopressin, the rats given the lowest dose or 500 mg per kilogram of methanol extract had the lowest total urine output, percentage of urinary excretion, and saline solution excreted. It also significantly reduced urine output by 45% compared to the control group. Linear regression analysis showed that the antidiuretic activity of the methanolic extract is inversely dose-dependent and moderate. The study also does not support the claim made by Sri Lankan traditional medicine that it is a potent oral diuretic. We will now be discussing my proposed innovations for the procedure. I would first like to mention that the oldest reference I found to have been utilizing this procedure using rats is a comparison of different variations of the method done by George C. Ham in 1943. The method has already been modified and optimized by various researchers for decades, especially on the hydration of the rats, the rat model and sex, and frequency of measuring diuresis. The first proposed innovation would be to introduce a variation in temperature. In a study by Ito in 1954, he found that antidiuretic activity of serum may increase upon exposure to heat and decrease upon exposure to a cold setting. Although studies on the varying diuresis in different temperatures have been made on different animals, like Azahan et al., and the use of Faust in their procedure in 1979, the use of varying temperatures on rats for new interventions is yet to be done. Varying temperatures will also involve manipulation of length of exposures to the different temperatures. This test will see how temperature can affect the antidiuretic potency of the intervention. Geographic locations of patients taking the antidiuretics may also affect their body temperatures, affecting the pharmacokinetics of the drug. Future studies on the antidiuretic activity of proposed interventions may consider use of 3 temperature settings. This study did not explicitly state how the urine collection procedure was performed, but previous studies of one of the authors, Ratnasooriya, employed the use of metabolic cages. In the illustration provided, metabolic cages have a mechanism which involves having an attached funnel connected to a receiver for the urine of rats. This method is highly convenient for measuring the urine outputs of the rats, as graduated glassware may be used. Although convenient, the use of these cages is not cost-effective because they are expensive and may also be difficult to procure in the Philippines. It is even more expensive for studies that will be using a high number of animal samples. A solution to this would be lining the floor of regular individual cages or compartments with plastic wrap prior to placing the rats. Urine collection may be done by extracting urine samples from the floor of individual cages or compartments using syringes. This method may be tedious, but is an economical alternative to purchasing multiple metabolic cages because the rats can be placed in individualized compartments in a large cage. This marks the end of my presentation. Here are my references for this simple but useful bioassay method. Thank you all for listening.